Hello everyone. In this video we will look at a thermochemistry topic that's very important in general chemistry, and that is the direct method of heat summation. Okay, so we have a question that we're going to try out. The question says, estimate the standard enthalpy of formation of CCl2F2 in the gaseous state. So the first thing you want to do, and by the way I am kneeling down, so I hope that's okay. The first thing you want to do is to write an equation to guide what you're going to do. So we'll say that this is the answer 1 to question 1. Let's write down an equation. So we have carbon, which typically when you start this type of question you write as a solid, and there are two forms of solid carbon, diamond and graphite. The thermodynamically stable one is graphite, so GR stands for graphite. So the same as a carbon pencil. And chlorine gas and fluorine gas. And this is going to give our target chemical CCl2F2 gas. Okay, so we write down an equation. Next, we acknowledge that although this is the overall equation, we've overlooked some steps, some energy steps. So for example, we need to break this bond here. We've got a homodiatomic molecule here. We need to break it. We've got another homodiatomic molecule here. So if we're going to build pieces back together, we have to have pieces that are ready to be built, or pieces that are ready to be building blocks. We can't use fragments of other pieces. So an analogy would be, if you want to reclaim old bricks, you have to get all the old mortar off before you can build a new wall and put fresh mortar on. Okay, so we need to strip this down of all its old energy components, which are the mortar. Okay, so let's start to do that. So if this is our overall equation, it implies that the carbon in the solid phase has graphite and chlorine in the gaseous phase and fluorine in the gaseous phase. Well, if we want to break this down, we have to convert this to carbon in the gaseous phase. We have to break this bond, so we have 2 lots of chlorine in the gaseous phase. So we've broken 1 Cl2 into 2 Cls. And we have 2 fluorines in the gaseous phase. Okay, so we're stripping our bricks away of all its old mortar. Now we want to take that carbon in the gaseous phase from here. We can add 2 lots of chlorine in the gaseous phase, and we can add 2 lots of fluorine in the gaseous phase, and we can build this together to make our target compound CCl2F2 in the gaseous phase. Okay, so let's look at this real quick. We'll call this equation 1 and 2. Let's call this equation 1. Let's call this equation 2. And we can see that we still get our net overall equation because we can cancel spectators. So if I combine equation 1 and 2 together, so we can say add 1 and 2. Okay, we add equations 1 and 2, then we can see the carbon in the gaseous phase here cancels carbon in the gaseous phase here. We can see that 2Cl gas cancels 2Cl gas over here. And 2 fluorine in the gaseous phase cancel 2 fluorine in the gaseous phase here. So we're just left with our original equation. Carbon solid, graphite, and a molecule of Cl2 in the gas phase, and a molecule of F2 in the gas phase. Net gives one molecule of CCl2, F2 in the gas phase. Okay. So although we've cancelled spectators, and although they don't appear in the overall equation, we have to account for the energy needed to do that. Okay. Now you would have access to a table in your textbook or in an assessment of atomization enthalpies and bond enthalpies. So all the numbers I'm going to use, you would have access to. That typically is an appendix in your textbook. So let's see how we would use those numbers. If we look at equation 1, so if we look at equation 1 from up here, we know that the enthalpy change from this equation, okay, so the heat energy needed to do equation 1 is going to be essentially the energy needed to make the products minus the energy needed to make the reactants. So this is going to be the standard enthalpy of formation of the products. And the products are carbon in the gas phase. I'm going to make 2 Cl, so I need twice the standard enthalpy of formation of Cl in the gas phase. The 2 here because there's 2 moles of Cl. The 1 here because there's only 1 mole of carbon. And 2 lots of the standard enthalpy of formation of F in the gas phase. That's going to give me, again, if I look at it, the values in a table, 716.7 kilojoules plus twice the value I find for chlorine, which is going to be 2 lots of 121.7 kilojoules plus twice the value I find for fluorine, which is 79.0 kilojoules, all in units of kilojoule. And this equals 1118.1 kilojoules. And I give 1 decimal place because I'm adding, and I'm adding numbers that each have 1 decimal place, and I propagate least decimals. If I then turn to equation 2, now I'm taking these raw ingredients and I'm making something out of them. So whenever elements come together, you're going to release energy. So if I look at the products initially, I know it's by definition going to be a release of energy. So I can a priori write a negative sign here. Think of your hands, think of any object when it comes together, your hands for example. You hear sound energy, there's a release of energy. Atoms wouldn't make sound energy, but they would make energy elsewhere on the energy spectrum, and that would correlate to enthalpy. Okay, so we have negative a priori because there's a release of energy. So basically, what am I doing here? I'm making 2 Cl bonds, 2 bonds between carbon and chlorine. So I've got twice the number of bonds, or the bond energy linking carbon and chlorine. That value is 328, so I have 2 of those. And I'm going to make 2 bonds of between carbon and fluorine. So 2 bonds from carbon to chlorine, shown here. 2 bonds from carbon to fluorine. So that's going to be twice the bond enthalpy for carbon to fluorine. Again, these values would be found from a table. I add those together, it's going to be a net negative value, and that is negative 1,538 kilojoules. No decimals this time because I'm adding and neither of my values has a decimal. This value represents the carbon to chlorine bond. This value represents the carbon to fluorine bond. Okay, and finally, because it is the direct method of heat summation, I'm going to add them together. So delta H1 plus delta H2 is the overall enthalpy, because I'm adding the heats. So this is going to be negative 1,538 plus our other value, which is 1118.1, and everything is in units of kilojoule. And this gives me negative 419.9. I can't give a decimal in my answer because I have no decimals here, and when I add, I'm propagating least decimals. So I know I'm going to have to round that, so I give 1 or 2 extra non-significant values. I know that the 9 is going to add 1 to the 19, so that's going to leave me with negative 420 kilojoules as my final answer. Now, if I want to give 3 sig figs, I would preferentially write this, because right now the 0 is not significant. You can add a dot here, which some people do to make that 0 significant. I personally don't like that, so I would rather write negative 4.20, so write it in scientific notation, by 10 to the 2 kilojoules. And I would suggest you present that in scientific notation. Okay, so this is our first new topic in thermochemistry, the direct method of heat summation. We'll look at a second example in a second. Before we do, let's just remind each other what we're doing. First of all, it's called the direct method. It contrasts with Hess's law of heat summation, which is known as the indirect method. It's called the direct method because we're directly looking at essentially every bond. So we're looking at all the energy components of every reactant and product directly, and we're adding them up. And we have an energy, a positive energy pile, a negative energy pile, and we look at both of them together to get the net energy pile. We're using the fact that energy can neither be created nor destroyed, so we're looking at conservation of energy, which we know is under the purview of the first law of thermodynamics, so that's what we're considering. So yeah, we're directly looking at everything and we're adding them together, but you can see that we really have to look at everything. We have to look at we have to critically look at where any step that can cost energy, we have to account for that. And I used an analogy that, we're looking at the strength of a brick wall. We have to look at the energy needed to make the bricks, the energy needed to make the wall, and this overall energy of the brick wall. And then we're incorporating both of those together. And if we use reclaimed bricks, we have to look at the energy needed to clean the bricks and scrape all the mortar off the bricks. So there's lots of analogies you can use to guide you through what you're doing. Okay, so this is our first example. I'm going to erase this, and then I have a second example ready for you. So bear with me 1 second while we erase this one. Okay, our second question, the second question I have ready for you, is similar to the first one. It says estimate the standard enthalpy of formation of CCl3F. So similar to the first one, but we have one more chlorine atom and one fewer fluorine atom. Okay, so this is question 2. So our answer to, we're going to use the same idea, so we're going to build some muscle memory here. We have carbon, which typically presents as a solid in the graphite form. And now I have 3/2 lots of the chlorine molecule in the gaseous phase. Notice I only have 3 Cl's, but it comes in pockets of 2 Cl's. So if I have 3 halves, I have 2 3s are 6, divided by 2 is 3 Cl's, so that's why it's 3/2 Cl. I only need 1 F, but it comes as a packet of F2. So I need a half a mole's worth of F2. And this will give me CCl3F in the gaseous phase. So that's my master equation, but there's hidden energy there that I have to account for when I do this calculation. So similar to last time, I'm going to look at every individual step. So I'll take my carbon as a solid in its graphite form. I'm going to add that to 3 halves a Cl2 molecule and a half a molecule, or a half a mole's worth of full molecules. I shouldn't really say half a molecule. I should say half a mole's worth of full molecules. That would be much more accurate. Okay, and this is going to give me carbon in the gaseous phase. 3 halves of Cl2 is going to break down into 3 Cl atoms in the gaseous phase. And a half a mole's worth of F2 is just going to give me 1 mole worth of F atoms. All right, let's call this equation 1. Okay, so notice it's balanced in terms of mass. That's very important. And then I'm going to take, for equation 2, I'm going to take the product from equation 1, so carbon in the gas phase, and 3 lots of Cl in the gas phase, and my 1 atom of fluorine in the gas phase, and I'm going to make my target product, CCl3F in the gas phase. Okay, so almost identical to last time. Again, the purpose here is just to build up some muscle memory. Let's take equation 1. Well, first of all, before we take equation 1, let's make sure we can see what we've done here. We can eliminate spectator ions. I've got carbon gas on both sides. I've got 3Cl gas on both sides, and I've got F on both sides. So we can see that overall, when we combine equation 1 and 2, which we will, we have only what's in our net target equation. Okay, so we're not changing anything net. All we're doing here is looking with a fine microscope at the energy pieces, and we're making sure that we add all the discrete energy pieces. Okay, so for equation 1, we need to calculate the enthalpy change for equation 1. And this is going to be the the standard enthalpy of formation of carbon in the gaseous phase. So how much energy is needed to make carbon a gas? We have to account for that. How much energy is needed to make 3 lots of chlorine as a gas? So we need 3 times the standard enthalpy of formation of gaseous chlorine. And we need how much energy is needed to make fluorine in the gas phase. Okay. You would be provided with a table, or in a homework question you'd have to look at the appendix in your textbook. So we find this value is 716.7. We need 3 lots of this, so we find the value, then we multiply it by 3, 121.7, and then we find the fluorine value as 79.0 units of kilojoule, and we quantify that as 1160.8 kilojoule. Again, we give 1 decimal because we're adding and we propagate least decimals, and you can see here that the values are all given to 1 decimal. Okay, looking at equation 2, let's calculate that component of energy. Equation 2, again, we know that when these atoms come together to make the target compound, they're going to release energy, so we know a priori that's going to be a negative value. So we can preface this with a negative sign. And then I've got 3 lots of a carbon-chlorine bond, which is 328 kilojoule. So this is the carbon-chlorine bond. I know I have 3 of them, so the energy locked in this bond, 3 of them because they're here, is 3 lots of that. And I've also got 1 carbon-fluorine bond, which is just 441 kilojoule. That's carbon-fluorine. I have 1 of them. The whole thing will have unit of kilojoule. So that's equal to negative 1425 kilojoule. Here we've got no decimals because we have addition, and we have addition of numbers with no decimals, so we preserve 0 decimals. Finally, because we're looking at heat summation, we can look at enthalpy of step 1 plus the enthalpy of step 2. And that's just going to be negative 1425 plus 1160.8. The whole thing has units of kilojoule. And that's going to give negative 264.2 kilojoule, but I can't give, I'm not allowed to give any decimals because this value has no decimals, and I'm adding and I have to preserve least decimals. So I'm going to use the next unrounded, the first non-significant digit to round the last significant digit. The 2 is less than 5, so I add 0 to the 4. So my final value is negative 264 kilojoules. Okay, so that's our second example of the direct method. I have one more example, and then I was going to recap some maybe 1 or 2 examples of the indirect method, just to contrast in the same video with the direct method. So I'm going to erase this very quickly, and then we'll look at our third and final example of the direct method. Okay, so the third and final example I have ready for you for the direct method. So question 3. Estimate the change in enthalpy for the following reaction. So we're given C3H8, the gaseous phase, so propane, and 5 lots of oxygen, so we know it's a combustion reaction, which means it's also a redox reaction. Gives 3 lots of CO2 gas and 4 lots of water gas. Okay, so what's the energy of that reaction? Let's do it. Well, first of all, before we do it, let's think about why it might be important. Why would you want to do, so you set fire to propane and you want to see how much heat is given off, how much enthalpy is given off. That could be to quantify the use of this as a suitable fuel. Let's say you wanted propane to replace gasoline in an internal combustion engine. Well, you want to make sure that you can drive the piston up and down rather than make the engine explode. So there's certain tolerances that fuels have to work in an engine and not destroy the engine. And this might be something that you would do to see if your new fuel, your novel fuel, is in the right tolerance range as a potential substitute for a volatile organic. Okay, so let's have a look. We've got answer 3. Okay, so here, everything's a compound. We don't have any atoms that we have to atomize or what have you, so let's have a look. And again, we're after the overall enthalpy change. So I know that the enthalpy change under standard conditions, well, first of all, I know a priori it's combustion. And I know that when I produce, well, first of all, a priori, I can predict this is going to be exothermic because I know net energy is going to exit the system, so I know my final answer has to be negative. So I can keep a lookout for that. But before that, though, I know that to make carbon dioxide, carbon and oxygen have to come together, they have to collide, and there's going to be a release of energy. So I know that a priori that release is going to be negative. So in 3 moles of CO2, I have 6 bonds between carbon and oxygen. So carbon dioxide has 2 double bonds between carbon and oxygen. I have 3 such molecules, so 2 by 3 is 6. So I have 6 lots of the bond enthalpy between C and O. And I have, well, water molecule has 2 oxygen bonds to hydrogen. I've got 4 molecules worth, so 2 by 4 is 8. So I have 8 HO single bonds. Okay, so that's my products. And now I'm going to add that to my reactants. Well, my reactants are going to be added, but they're going to a priori be positive. So essentially I've got to subtract the energy needed to make my reactants from the energy delivered by my products. So it's almost like profit. The products are like profit and the reactants are like expenses. To look at the net performance of a company, you have to subtract the expenses from the profit. Okay, so we have 2 lots of carbon-carbon bond. So I've got 3 carbons here. There's 2 bonds connecting 3 carbons because the one in the middle bonds to its left, that's 1 bond. It also bonds to its right. That's a second bond. So again, 3 carbon atoms are bonded, incorporate 2 carbon bonds. And I have 8 bonds between hydrogen and carbon. So that's 8 lots of the bond between carbon and hydrogen. And I also have 5 lots of the bond between oxygen and itself. So 5 lots of the bond between oxygen and itself. And it's a double bond. Okay? So again, these are my products. 6 carbon double bonds in 3 molecules of CO2. 8 hydrogen single bonds with oxygen in 4 molecules of H2O. Negative a priori, because they're going to come together and release energy, but I've got to incorporate the energy needed initially to make my reactants. It's going to cost energy, positive applied throughout. 2 carbon bonds between 3 carbon atoms here. 8 bonds between carbon and hydrogen here. And 5 bonds here between 2 oxygen atoms. Okay, we get these values from a table in our textbook. They would be provided to you in an assessment. So this is going to be negative. 6 lots of that value are going to be 4, 3, 6, 8. And 8 lots of that value are going to be 3, 7, 0, 4. And then 2 lots of that value are going to be 6, 9, 6. And 8 lots of that value are going to be 3, 3, 0, 4. And 5 lots of that value are going to be 2, 4, 9, 0. The whole thing is going to have units of kilojoules. We add those up because it's direct method of heat summation. Negative 1582 kilojoules. So overall, we know that this process net is exothermic. Remember, that means that energy exits the system. This means that if we measure the temperature, which we could do in the lab, when we measure the temperature, we always measure the temperature of the surrounding. The temperature of the surrounding increases. So we would see clearly if we burn propane, it generates heat energy and the surrounding gets hot. Its temperature increases. Okay, that concludes the third and final example I had prepared for you for the direct method, to alert you that this is an important content topic in thermochemistry, so practice some of those. I'd like to do just a couple of things on Hess's law. We've looked at it already, the indirect method. I think it'd be nice to put it in the same video to immediately contrast it with the direct method. Okay, so let's just have a look at a couple of examples of Hess's law. I'll try and keep this video to under an hour. I'd rather have multiples of hour videos than a big long 2 or 3 hour video. Less likely things will go wrong then as well. Okay, so I'll erase this. We'll look at maybe 1 or 2 examples of Hess's law. So this is the indirect method. Remember, we call this Hess's Law. It's where we don't know all the information we need, so we're going to indirectly gather it. Okay. I'm not 100. I don't think we've looked at this already, so hopefully this is a new example. But let's have a look. So the question is calculate. Notice I'm saying calculate here, and in the direct method I said estimate. We should probably comment on that in a second. That's not a trivial distinction. It's actually an important distinction. Let's comment on it now. We say calculate with the indirect method because we can actually calculate a value for an absolute value for a given situation. We say estimate with the direct method because we're using bond enthalpies. Now, bond enthalpies depend on their environment. So we use average values, and average values typically have up to a 10% deviation. So you can look at the bond strength of a carbon-hydrogen bond, and in one molecule, look at it in a different molecule, and it will be subtly different. If you take an infinite number of molecules, potentially there's around a 10% deviation. So we're always getting an estimate. We're never getting an exact value. So these words they mean something. They're not used nonchalantly. Okay, so calculate the reaction enthalpy in the following reaction. So we've got N2O gas and NO2 gas to give 3NO gas. So that's our target equation. We're given some information. We're told that we're given reaction A. We're told that there's a reaction that's known where 2NO gas and oxygen gas can give 2NO2 gas. And this particular reaction has an enthalpy change of negative 113.1 kilojoules. We're given another equation, B, that's known where a molecule of N2 gas and a molecule of oxygen gas come together to give 2 lots of nitrogen monoxide gas. And this particular enthalpy is positive 182.6 kilojoules. And we're given a third piece of information, a third known equation. 2 lots of N2O gas is known to give 2 lots of N2 gas and oxygen gas. And this particular reaction has an enthalpy of negative 163.2 kilojoules. Okay. Just gonna grab my coffee real quick. Fuel the chemistry. Add the human element to the presentation. If you can hear screaming in the background, I'm at home during the coronavirus pandemic and my 3-year-old shouting at my wife in the other room. So I apologize for that. Everyone's safe in the house. Okay, so we've got a target. We've been offered basically a puzzle to solve and puzzle pieces. What can you do with the puzzle pieces? You can scale them, you can multiply them, you can divide them, you can rotate them. If you rotate them, you have to change the sign of the enthalpy value. So here's what we're going to do. Our job is to make sure we can find these three items in our puzzle pieces. So I'm going to circle them in red. N2O, I can see N2O here. NO, let's see, C, B, let's see, NO, yeah, I can see NO over here. So notice my N2O is in the right place, but I've got too much. My NO is in the right place, but I don't have enough. And my NO2 is in the wrong place, and I have too much. So I've got the components I need, but they're just not in the right place at the moment. So what I'm going to do, my solution is to take A, divide it by 2. Why divide it by 2? Well, equation A has NO2. I need one of them, but it offers me 2 of them. So I need to divide by 2 to get to basically scale down. But I need NO2 as a reactant, not a product, so I need to reverse. So I'm going to take A, divide it by 2, and then reverse it. B, B I don't want to do anything to at all, and I'll tell you why. I need NO. I don't have enough, but when I reverse A and divide by 2, I get one additional NO over here, which is going to give me the 3 NO I need. So I don't want to do anything to B, so I'm just going to keep it as is. C, what do I want to do with C? Well, I just want to divide by 2 because I don't want to reverse because N2O is in the right spot. It's a reactant. If I reverse it, I'll make it a product, and I don't want to do that. But I need one of them, and I have 2 of them, so I need to divide by 2. So I'm just going to take C and divide by 2. So that's my to-do list. That's what I want to do. If I actually write that, so let's say A divided by 2, if I rewrite that real quick, that would be, let's call that A prime. Let's keep this as B because that never changed. Let's call this C prime. Okay. So then let's write A prime. That's going to be, let's say, just divided by 2. Then reversed. Okay, so it's going to be NO2 gas gives NO gas and a half O2 gas. Okay, now I also need to reverse the enthalpy of A, so make it positive and then divide by 2. So that's going to give me a new enthalpy value that's positive, and it's positive 56.55 kilojoules. So you take negative 113.1, reverse it to make it positive, and then divide by 2. I'm just going to keep B, so I'll just rewrite B same way. So N2 gas and O2 gas to give 2 NO gas. And I'll just rewrite the enthalpy value. Enthalpy is positive 182.6 kilojoules. Then I divided C by 2, so let's call that C prime. So C divided by 2 is just going to be N2O gas to give N2 gas and a half O2 gas. And the enthalpy here is going to be negative 163.2 divided by 2, which is negative 81.6 kilojoules. I can now cancel spectators, so I can see I have an N2 gas as a reactant here and as a product here, so that cancels. I can see I have a half oxygen here, another half, so I've got 1 mole of oxygen here as a product. That cancels the 1 mole of oxygen here as a reactant. And I'm left with just the chemicals I need. I've got NO2. I've got N2O. That's another one I need as my sole surviving reactants. And my products, I've got 1 lot of NO and 2 lots of NO. So I've got 3 total moles of NO as my sole surviving product. Okay. So now I can calculate the enthalpy. The standard enthalpy is just going to be the sum, because I'm still doing heat of summation. I'm just going to add these values together. So it's going to be the enthalpy of A prime and the enthalpy of B and the enthalpy of our C prime, which is 56.55 plus 182.6 plus negative 81.6. All units are kilojoule. Gives me a final value of positive 157.6 kilojoules. Okay, and because I'm adding things with 2 decimals and 1 decimal, I have to preserve the lowest decimal, so I give this as 1 decimal. Okay, so that was another example of the indirect method, or Hess's law. We'll just do one more example of the indirect method, again, as a direct comparison with the previous direct method. We'll call this question 2. Again, calculate the reaction enthalpy for the following reaction. We've got 3 H2 gas and ozone gas, so not oxygen but ozone, O3, to give water. So So that's our puzzle we need to solve. What's the enthalpy change for that? What's the, how much energy is exchanged during that process? And we're given some information. We're given A and B. We're given information that 2 lots of H2 gas and oxygen can come together to make 2 lots of water. And we're told that this energy change, or enthalpy change I should say, is minus 483.6 kilojoules. We're also given information about oxygen. We're told that 3 lots of oxygen can come together. Well, actually cannot come together, can just directly produce 2 lots of ozone. And we're told that this enthalpy change is positive 285.4 kilojoules. So that's the information we're given. We now need to come up with a plan. If we look at the information we're being given, I can see that I need hydrogen as a reactant. I have it, but I only have 2 of them and I need 3. So I need to multiply equation A by 3/2. So to AK and multiply by 3/2, that'll give me an extra H that I need. If I look at B, I need ozone as a reactant. I've got ozone as a product. So I need to reverse B, and then I need to divide by 2 because I only need 1 ozone and I have 2. So I need to reverse B, then divide by 2. Let's say this is going to give me A prime, and this is going to give me B prime. Okay, so let's write A prime and B prime. So A prime, so I'm multiplying it by 3/2. Okay, so I've got 2H2 multiplied by 3/2. So that's going to give me 3H2. 3/2 is 1.5, so I'm multiplying 2 by 1.5, which gives me 3. Multiply 1 by 1.5, I just get 1.5, or 3/2 oxygen. And I get 3H2O. I've got to multiply the enthalpy by 3/2. So essentially just scale negative 483.6 by 1.5 and you get negative 725.4 kilojoules. Then you take equation B, you've reversed it, you've divided it by 2, so you just get 1 lot of ozone gives 3/2 lots of oxygen. You scale delta H by 3/2 in reverse, We reverse 285.4 to make it negative. Then we scale it by, we scale it by 3/2. We divide it by 2. So 3 divided by 2 is 3/2. So we halve the number, so we get negative 142.7. Okay. Now we're just going to add them together. So I know that the overall enthalpy change is going to be the enthalpy change of our A prime and the enthalpy change of our B prime. So this is going to be our negative 725.4 value plus our negative 142.7 value, all in units of kilojoule, which gives us negative 868.1 kilojoules is our final answer. Again, I'm adding, so I propagate least decimals. I've got 1 decimal in both objects I'm adding, so I round my total value to 1 decimal. Okay, so this directly contrasts with the direct method. This is the indirect method. Again, it's indirect because we're approaching a problem indirectly from other known equations. We're not head-on looking at the bonds in a hydrogen molecule. We're indirectly noting that we can cancel spectators. So we can see if we look at A prime and B prime, 3/2 oxygen are reactant and product, so they cancel. We've got 3 hydrogen molecules, 1 ozone molecule, 3 water molecules as our final product. And the energy of adding those pieces together is the summation part. Okay, we're coming up to the hour, so this will conclude a video on the direct method of heat summation and the indirect method of heat summation.